we are going to see about a topic normalized cut. It is again a segmentation approach. So previously we have seen split and merge and mean shift. So split and merge is completely based on merging the similar pixels. Mean shift means again it's like a clustering of pixels. We'll compute the pixels and we'll try to group so that it can form a segmentation. Normalized cut means it is basically based on the graphs. So normalized cut technique look how strongly the pixels are connected, and we'll try to separate the groups that are weakly connected. So here look at the graph, we have two set of groups, one is A, another one is B. Pixels in group A are strongly connected to each other, and the pixels in group B are strongly connected, but the connection between the groups are weak. The strong connections are represented as red color nodes, red color edges, and the weak connections are represented as blue color edges. So we will divide the weak connections. So on dividing the weak connections, we can get the two exact groups, that is two segmentation of an individual image. Look at this table. So we have two groups A as well as B. Here what they have mentioned is association of A comma A. Association of A comma A means sum of the weight of edge within group A. We have around 1, 2, 3, 4, 5, 6, around 6 edges are there. Each edge will have weight. Sum of all the weights of edges in a group A is known as association of A comma B. And here we have three edges. Each edge will have a weight. Weight is nothing but number. You might be aware of it when you learn data structures, right? So each edge will have a weight. So sum of the weight within the group B is association of B comma B. And cut of A comma B and cut of B comma A both are similar because sum of weight of edge between group A and group B. So A and B and A both are associated, they are same. And association of A comma B and association of B comma B means total connections of A to all node is A comma B. Total connection of A inside A as well as to other B. So look at here 1, 2, 3, 4, 5, 6 inside A, and to other node 1, 2, 3, 4. So 5 plus 4 we have 9. Similarly, check for association of B comma B. Total connection of B to all node. Inside B and 2A is calculated. Inside B 1, 2, 3 and 2A 1, 2, 3, 4. So 4 plus 3 7. So association of A comma will be A comma B will be 9. Association of B comma B will be 7. So this is the matrix. A tabular form of association and the cut for the graph is represented here. So a simple cut. We'll see normalized cut later. Now first let us say a simple cut between two groups is represented as summation of I belongs to A and J belongs to B, W of Ij. Based on the edge only, based on the edge weight only, we are coming to the conclusion that whether it is a weaker one or stronger connections. So if it is a weaker connection, we'll divide it. So W of Ij represents the similarity between the pixels. So based on the similarity, the higher similarity leads to the stronger connection, and the lower similarity between the nodes or weaker connection, we will divide it. Using just the minimum cut is not effective because it isolates even a single pixel, or it may be result in a smaller region of segmentation. This is often not a good practice. So to solve this, a normalized cut is proposed. So normalized cut, which not only measures how disconnected the graphs but also considers how strongly each group is connected to the rest of the graphs, rest of the groups. Normalize cut of A comma B equal to cut of A comma B divided by association of A comma B plus cut of A comma B divided by cut association of B comma B. You know this value as well as this value from the table. From the table we can get this value. On applying this formula we'll get a normalized cut. After the result, as a result of the normalized cut, this ensures that we only separate a group if the connection between them are weak relative to the internal connections. This criterion balances both between group disconnection as well as within group associations. So, computing this exact optimal normalized cut is NP complete. We'll take entire graph and we'll form the table. After forming the table, we'll apply the formula. If the graph is very large, then it will become computationally infeasible. So it is called as NP complete problem. So to make it easier, to make it simple, we are going to convert the same problem into an eigenvalue problem. So normalized cut problem can be written as this formula, when y transpose d minus w into y divided by y transpose dy. Further, we are minimizing this equivalent to solving the generalized eigenvalue problem as d minus w into y equal to lambda into dy, where W is the affinity matrix, D is the diagonal matrix of row sum, and Y is the assignment vector. So based on the graph, we'll form the W matrix, diagonal matrix, as well as the assignment vector. On applying this formula, we'll get some eigenvalue as well as eigenvectors. So simple, we are having a graph with so and so weights. We are having two formulas. On applying this formula, we will get eigenvalues and eigenvectors. So the second smallest eigenvector of the system will determine the division. So second smallest value of the eigenvector is used to divide the graph into two groups. So see this. This is a matrix. So a sample 32 cross 32 matrix with weight W. The W matrix is given here, and after applying this into the formula, the diagonal elements, and on applying the assignment vector, we, as I said, right, we'll get eigenvalues as well as eigenvector. The second smallest eigenvectors are represented like this. So the eigenvector corresponding to the second smallest eigenvalue of generalized eigenvalue problem is given here. So this, following this line, will divide the entire image into two. Okay, this is a sample image. After applying smoothing, we have so and so weight matrix, right? So by applying the previously said formula, we got eigenvalue as well as eigenvector. So the second smallest eigenvector is represented here. On following this, we'll divide the image into two parts. So we got the result of segmentation. And again, here the complete image is shown here. This is the original image. First, we'll compute the eigenvalue and eigenvector for the given image, which will divide eigenvalue and eigenvector will have positive value, negative value, small set of positive values and large set of negative values. So and so different groups would be there. Initially, we'll divide the group into two parts, and then we'll again repeat the process, and we'll further repeat the segmentation. That is what mentioned in the above diagram. Then affinity definition. The pixel affinities are often computed using both feature similarity as well as spatial closeness. So we are having a formula Wij is refined as exponentiation of so and so. This f of ij represents the feature vector, and xi and xj represents the spatial coordinates of pixels. The difference represents how pixels differ their features are, and xi minus xj represents how far apart they are in the image, and sigma f and sigma s represents the scaling parameters, and r is the maximum neighborhood radius. If two pixels are very close, then w of ij would be equivalent to 1. And this part is contour based similarity. This is completely based on features. F is a feature, right? So next we are going to take a contour. Contour means exact edges, right? Contour based similarity. The w of ij is rewritten as w of ic, which is based on pcon. Pcon means the probability of contour. Contour means edge, right? The probability of contour at position x. If you are given a position x, we'll check whether there is a possibility of any edge or there, or we can identify where it is a simple region apart from edge. So probability of contour at position of x will determine the contour based similarity. The final affinity matrix will combine both the feature similarity as well as a contour based similarity. A drawback of normalized cut is that it requires solving large eigenvalue problems, which can be slow. So far we have seen is we have taken a simple cut, and then we have made it into a normalized cut. Normalized cut would be NP complete, computationally infeasible. So we have moved to eigenvalue and eigenvector, and now again eigenvalue and eigenvector is computationally expensive when compared. It is inexpensive when compared to NP hard, but again eigenvalues and eigenvectors are computationally expensive, which can be further reduced. The technique is called SWA, that is weighted average, weighted aggregation. We are going to see only very simple four steps. We will not take the entire image. We will convert the entire image into the coarse details. In image pyramid, we know fine level details and coarse level details. Fine level details represents the entire image. Coarse level details represents only the finer part of the details or only the important part of the details. So first step, we need to convert the fine image into the coarse image. And then we'll create an interpolation matrix. Interpolation matrix is used to produce a normalized cut on only the core pixels. After identifying the interpolation matrix and performed the normalized cut, we'll perform the similarity test. So we will add any texture or color or any features. If there is any features means we'll analyze that too. Then finally we'll convert the course details back to the finer details. This is SWA technique. So the comparison of multiple segmentation technique is shown here. So normalized cut, and this is the some other process which is more advanced than SWA one. SWA. So normalized cut, mean shift segmentation, and SWA segmentation, and combining all these is that we will get a better segmentation. So normalized cut is one of the technique used to divide the image or segment the image. Thank you.